And so, good morning, ladies and gentlemen. Time to return
Morning,
to
ma'am.
mathematics. Questions already? No. All right, so time to return to mathematics. So we have equations of a line in space today. Up to this moment, we did equations of a plane in space. That was last time. Before that, we worked only in the two-dimensional plane in analytical geometry. So last time on Friday, we moved to the space, looking at planes. And now we will be looking at the equations of lines. Interestingly, we started first of all with planes and then we moved on to lines. That's because actually some equations of a line do involve equations of a plane as well. So we started with planes, now we are doing lines today, and next time, that is on Wednesday, we will have a look at combinations. How can we combine lines and planes to solve questions, let's say, about space? So first of all, we look at the planes separately, at lines separately, and then next time we will combine them and see how to deal with the lines and planes in 3 dimensions taken together. And so I am actually, again, as always, switching off my video because otherwise it takes up some space on my screen. I can't afford that. I need the screen. I do hope that, let me see. Let me see, 13 people in the chat, but more than that online. Okay, that's up to you. That's up to you. I can only note when you write your name in the chat. So if you just decide to switch on the computer and disappear, that's up to you. That's up to you. I'm not counting people who are online. I'm not looking at that. And so, okay, I'm sorry. It looks like my tablet connection is a little bit shaky. Now it's better. And so let's have a look at equations of a line in 3 dimensions in space. There we go. There we go. So first of all, let's remember what an equation of a plane in space looks like, because we already discussed that for one lesson. So everything else we have been revising and reminding you, but equations of a plane in space was just last time. So let's start with let's have a look at what equations of a plane in space are possible. So remember that we had an equation using the normal vector, that is the vector that was perpendicular to the plane, and a point in the plane. So in principle, it would look like something like we have a plane. We have, okay, all right, sorry about this. We have a normal vector, a vector that is perpendicular to this plane. And some point, we usually put that normal vector at that point, but it didn't matter really. So we have this point M, we have this normal vector of a plane, and this information is absolutely enough to write an equation of a plane. Then, of course, the next possibility would be if we open up the parentheses, we get the general equation of a plane, meaning that all those constants that are not multiplied by x, y, z can be combined. And so we get a constant d, which does not have any specific meaning of distance or anything else about a plane. And then we had this crazy looking equation that was the plane through 3 points where x1, y1, z1, x2, y2, z2, x3, y3, z3 are all points, known points in the plane. So in this case, we are assuming that we have a plane and we have 3 points that are not on the same line. We have 3 points in this plane, and then through these 3 points, if we know the coordinates of these 3 non-collinear points, we can write a general equation in this form. However, please remember last time we also discussed this possibility, or rather I discussed and hoped that someone is possibly listening. So we thought perhaps we can write to, okay, I need to move my hand a little bit differently. Okay, I will improve. I will improve because this is okay. Back to pen, and there we go. 1 and 2. So it was also possible to write down two vectors from between these three non-collinear points, for example, M1, M2, and M1, M3. And when we write down these two vectors, then we could find the vector product of these two vectors and thus get a possible normal vector as the vector product of two vectors from that plane. Because you remember that the vector product is a vector that is perpendicular to those two vectors. And finally, the plane through the three intersects, okay, the equation of a plane through three intersects of the coordinate axis, which would look like this somewhat. So if we have this plane, then we have three points on the axis that look like this. These are the 3 points where the plane is supposed to intersect these axes. A on the x-axis, B value on the y-axis, and C on the z-axis. And so we can imagine the plane that cuts, okay, or a triangle is cut out of the plane in the corner between the three axes of coordinates. But of course, we understand that the plane itself is greater. We know that planes are infinite after all. But if we consider just the corner between the three axes of coordinates, then we can imagine that the axis or the planes of coordinates, actually they cut out like something like a triangle of this plane, and this is where the three values A, B, C come in. So those are the intersection points with the three axes. Okay, this much about the equations of a plane. And now we will consider the equations, possible equations indeed, of a line in space. And excuse me for a minute, I need to close the door of the classroom. And so, vector equation of a line. We will suppose that we have a line, and then how to describe the line in 3 dimensions. We already did that in 2 dimensions. So let's suppose that we have a point on the line, one point that we know on the line. Let's call it A. I will actually mark it as A, point A, with coordinates, say, x0, y0, z0. Then we need to know something else. One point is not enough. We need to know either another point on this line or maybe the direction. And in fact, just like in 2 dimensions, we were thinking about the direction of the line. So we will do exactly the same in 3 dimensions. So suppose we have a direction vector of the line, a direction vector S. Again, coordinates known, 3 coordinates in this case, M and P. And to describe any point on this line, so that would be the point R. And just like in the case of 2 dimensions, it could be any point on this line. It could slide back and forth. It could actually slide along this line back and forth. So it's we can call it again the running point or the current point, or a random point on this line, just like we did with the plane. So any point on the line is given. And then we will suppose that, okay, we have the origin of coordinates somewhere, well, where it is supposed to be, and a couple of vectors. The position vector OA, that would be starting at the origin and going to the point A. So the vector OA, this is the position vector, and we also can write it as simply vector A. It has, remember, the same coordinates as the point A. That's why it's called the position vector. It starts at the origin, and therefore the coordinates of this vector are exactly the same as those of point A. And similarly, the radius vector or position vector of the point R, OR, which can also be written as vector R, lowercase. And we have to remember that the vector R has coordinates x, y, z, and these coordinates will, let's say, will be the coordinates of the point on the line. The same coordinates as in this case with the point R. And as I said, the vector coordinates of A are the same as the coordinates of the point, A capital. And now, just like in the two-dimensional case, we did note there that the vector AR can be written as the vector OA plus the vector AR. That doesn't matter here, even the, sorry, not AR, but OR, I'm very sorry, OR. The vector OR can be written like this. It doesn't matter where the points A and R are, actually. Remember that we could do this even without knowing where these points are. It's purely mechanical. From O to R, we could get, first of all, from O to A, and then from A to R. And then we remember that the vector AR is, in fact, collinear to the vector S, to the direction vector S, maybe in the same direction, maybe in the opposite direction, but that meant that the vector AR could be written as some number t times the vector S. The collinearity means that we can actually find some number, which, when multiplied by the vector S, gives us the vector AR. And as a result, we get this equation for a line, vector equation for a line, vector equation of a line, like this. So just written in terms of vectors, maybe not the most understandable thing, as long as our vectors are very abstract. R, vector R, some vector R, some vector A, some vector S. This might seem a little bit, well, not exactly confusing, perhaps, but at least, well, like more or less nothing. And that means we need to express it more clearly, and that would be in this form. The vector R is the vector from the origin to any point on the line. In other words, these would be the coordinates of any point, x, y, z, the coordinates of any point on the line. So the coordinates of any point on the line can be found if we take the coordinates. These are the coordinates of the point A on the line, although we write them as a vector. And you also should notice that I have written the vectors in the vertical form, in the column form in this case, because this is easier to read and understand this equation if you write the vector in the vertical form. If you write the vector horizontally, then it's a little bit more confusing. But if you write it vertically, you can see it line by line. You can see line by line how you can read each coordinate of the point. And of course, the M and P, these are the coordinates of the direction vector, which is multiplied by T. So in fact, this is better and more easily understandable than the equation in the very, very abstract form, because this, when you look at this, it means nothing. What's there? Maybe t, you can understand that t is a number, but if you don't know the vectors a and c, or if you do not see them in their coordinates, if you do not see them explicitly, then actually it doesn't make much sense even to write this equation. We can only use this equation when we have specific numbers. So when we have the point A with coordinates x0, y0, z0, when we have the coordinates of the direction vector s. Now, we can rewrite this, as you see, line by line for each coordinate separately. X evidently equals x0 plus t times m, y equals y0 plus t times n, and z will equal z0 plus t times p. So in fact, we can write the equation, an equation, for each coordinate separately. The interesting moment being that, of course, the t value must be exactly the same in all three cases. For all three coordinates, the t has to be the same because we are multiplying the parameter t by the whole vector m and p. So it's the same parameter, it's the same one. If this looks a little bit confusing, perhaps again, just letters, variables, please remember that x0, y0, z0 are numbers, and m and p are numbers. So in fact, you will have an equation for each of the coordinates x, y, z in the parametric form. Remember, we already had parametric equations of different curves. At the beginning of this chapter, at the beginning of this unit, we had parametric equations of curves. We had x depending on t, some kind of equation, y depending on t. Again, you get some kind of equation. So in principle, you are describing a curve that was in two dimensions. Depending on the value of parameter t. In the same way here, we are describing something in three dimensions. In this case, it will very definitely be an equation of a line. If you remember how we just constructed this equation, where we got it from, this is very typically an equation of a line, a linear equation, because you see the parameter t is only multiplied by some number. It's not squared, we don't divide by it, we don't take sines, cosines, nothing that complicated. So what we have here is an equation of a line, or rather three equations, parametric equations, plural, three of them, for each coordinate separately, parametric equations of a line. To see an example, let's have a look at an example. So these are x0, y0, z0, and this is the direction vector. So we could write it in the vector form, and that would be x, y, z in the vector form. It passes through the point 1, 2, 3. Remember that the coordinates of the point given are the first, then plus some parameter t times the direction vector 2 minus 1, 0. Or if we want to write it in the parametric form, x is 1 plus 2t. See how it's a linear equation because there are no squares, no division, no square roots, no higher powers, no sines, cosines, just a linear expression. Y equals 2 minus 1t, and z equals 3 plus 0t, so that's just 3. This means, in principle, that this particular line would be parallel to the xy plane, because the z coordinate is the same for all points of this line. So it's parallel to the XY plane. So here I have the same thing written, let's say in a printed form. It's exactly the same thing. You don't have to copy it once again, but we see how we can, if we know a point and we know the direction, then we can write both the vector equation that is in one piece using column vectors, or like this in the parametric form, which is perhaps also convenient. So what we should note, important things. Let's see, I'm going to do some highlighting now. Highlighter, and let's choose other colors. So you see that from the equations, whether it is the equation as the vector form, in the vector form, or in the parametric form, first of all, you can see the coordinates of one point on the line. You can see the coordinates of one point on the line. So if you have the point and the direction, you know how to write the equation immediately. If you have the equation or the parametric equations, in fact, you can also see the vector, the direction vector of this line, clearly readable from that equation. And of course, if you see that there's no t, as there's no t in the z coordinate in this example, for instance, that simply means that the third coordinate, or this coordinate of the direction vector, is 0, which means evidently parallel to the xy plane, perpendicular to the z-axis. That's what happens with this line. So these are two kinds of equations now. So now we have the vector equation, and we have the parametric equations. At this moment, I am erasing all ink so that I'm leaving only the things very clearly visible. So the vector equation, that would be the first two in different forms. Okay, pen, please give me the pen. And let's take white again. So this is the vector form, the vector equation. Even when the vector coordinates are written down openly. And this is the parametric equation, or these are the parametric equations, 3 of them, as you can see, 3 parametric equations. But to remember that t can be any real number. Yes, that's right. T can be any real number, but t has to be the same. T has to be the same for all 3 coordinates. Otherwise, it's not a point on the line. Now the next, canonical equations. So we still work with the parametric equations. So what we will do is, if t has to be the same, what would happen if we express the t value from the equations? Because you see, if t has to be the same for all 3 coordinates, then perhaps we can even find the t corresponding to each point on the line. So say we have a point on the line given, and we know the equation of the line, we can find the t value for this point. So we look at the coordinates and we see evidently Tm would be x minus x0, Tn would be y minus y0, and Tp would be z minus z0. That's something from each of the equations, right? And now if we express t from each part, then we see that t is x minus x0 divided by m from the first, but it also is y minus y0 divided by n from the second, and it also is z minus z0 divided by p from the third parametric equation. And this set of ratios, this is called the canonical equations. Again, plural. It's not the canonical equation, it's canonical equations, because you see you have at least 2 equalities. So you have one equation and the second equation. In fact, you could even imagine the third equation when you equate the first ratio and the third ratio. So that's why we are saying plural canonical equations. And this is, again, something official. So I am repeating this in the printed form, the same thing in printed form, the same thing I wrote. What you see in the canonical equations, again, you see very clearly and explicitly, you don't see the t, perhaps the parameter, but what you see is, again, the point x0, y0, z0, you see the coordinates very clearly from this, and you see the direction vector m and p very clearly in this. And of course, you should remember that we had a similar equation in 2 dimensions only. So for the line in 2 dimensions, for the line in the xy plane, we had this equation, and that was a single equation, one canonical equation. So now, yes, of course, we have to add a third coordinate. So inevitably, in fact, we get canonical equations, plural. And there we go. And there we go. These are the canonical equations of a line in 3 dimensions. So in this case, just like the vector equation explicitly written, or like the parametric equations, the numbers, as you see, are exactly the same. x0, y0, z0, same numbers, m and p, same numbers as before. So we have had 3 types of equations for a line in 3 dimensions. They all use the same numbers, the exactly same numbers. You will always, in these 3 kinds, be able to clearly see the coordinates of a point on the line. One point is evidently given, and the coordinates of the direction vector. You will always, in this form, be able to clearly see the direction of the line. So one example, the same, it's the same point, see, 1, 2, 3, same direction, 2 minus 1, 0. So we are just writing x minus 1 divided by 2, y minus 2 divided by minus 1, and z minus 3 over 0. Similarly to the previous case, we don't divide by 0. You don't have to worry about one of the coordinates, or even 2 of the coordinates of the direction vector being 0, because that happens. Those lines exist. We can imagine a line that is parallel to one of the axes or parallel to one of the coordinate planes, which means that 1 or even 2 of coordinates of the direction vector are zeros. But remember that we are not exactly required to perform division. What this means, this makes sense only if we have 0 over 0. If we have something else over 0, non-zero cannot be divided by 0, but the ratio of 2 zeros can be anything we want or need. And therefore, this makes sense only if z equals 0, which of course corresponds to our previous equations when we had z equal to 0 in the previous page. So this is what 0 in the denominator in this case does. It is not division by 0. Algebra does not allow us to divide by 0. This is not division by 0. It simply says the ratio of these 2 zeros is the same as the ratio in the x coordinates or the ratio in y coordinates. The ratio is the same, but it is only possible if we have 0 over 0. That is, if we have z equal to 0. That's the meaning of the 0 in the denominator in this case. We are not required to divide, so we don't have to worry about impossibility to divide by 0. Because we are not dividing by 0, we are simply stating this ratio will only make sense, any sense at all, if z is 3. And so the equations, of course, the same. And of course, if one or more of the coordinates of the point x0, y0, z0, if you have some negative numbers there, remember that you have to subtract these negative numbers, so you might get a plus. You might get a plus. So x plus a number means that the x coordinate of that point is negative. So pay attention to the signs. Don't confuse the order, the sequence, the numbers, the coordinates of vectors and coordinates of points, and so on and so on. So many people are late today, it seems. Okay, that was canonical equations, plural. Next, how to write an equation of a line through 2 points. So suppose we have these 2 points somewhere, and then we have to write the equation of a line through these 2 points. We would say, okay, if we have 1 point and the direction vector s, we are happy. The problem is here we have 2 points. So we can choose whichever of these 2 points we like to be the 1 point, but we need the direction vector. So yes, we have it. See, we have it. The direction vector could be the vector from M1 to M2, or if we like backwards from M2 to M1. But if we have 2 points on the line, we automatically have the direction vector. We automatically have the direction. All we have to do is write it. All we have to do is write it. So yes, the direction vector is the vector M1, M2. So that would be x2 minus x1. y2 minus y1 and z2 minus z1 as shown on screen. Yes, it could be backwards. It could be m2, m1. What's more, if you see that all the coordinates of this vector are, for example, divisible by some number, you can even take, okay, all coordinates can be divided by 3. So let's take the direction vector 3 times shorter. Let's divide this vector by 3 if coordinates are easily divisible by 3. Or if all coordinates are even numbers, let's divide everything by 2. So you can actually adjust, or if all coordinates of S happen to be negative, that's not so very nice. Let's multiply the vector S by -1. Let's make it in the opposite direction. So it's all possible because remember the length of the direction vector doesn't really matter. What we need is the direction, but the length could be shorter, could be longer, it could be this way, it could be that way. You can always adjust so that the equation becomes simpler. And then this is the canonical, these are the canonical equations, that's from the previous. So what do? We replace M and P by these differences. And of course, x0, y0, z0 could be replaced by either the coordinates of M1 or the coordinates of M2. So whichever you want to choose. As a result, the classical form for a line, for the equation of a line whose 2 points are given is this. So x minus x1, y minus y1, z minus z1, this part is simply according to the canonical equation, x, y, z minus coordinates of a known point on the line. You may choose the first point or the second point. It doesn't really matter much, but let's say to get a nice standard form for the equation, let's choose x1, y1, z1 as the first point, and then you have x minus x1, x2 minus x1, y minus y1, y2 minus y1, z minus z1, z2 minus z1. Easily. So some kind of order. At the same time, let's remember that you may choose the first point, the known point, to be whichever of the two you like. And here, of course, you have the direction vector. You can express this direction vector separately. You don't have to write this equation from scratch like this. You don't have to write it from scratch like this. You can say, okay, let's first of all find the direction vector S separately, vector M1, M2, or AB, if you like, whatever the names of these points are, and then just write the canonical equations using that vector. However, this is something that you can use again as a template. Remember, I like to compare these standard types of equations as templates. We choose the template that we need, and we need the template according to what we have, what information we possess. And finally, the third type of fifth type of equation of a line. We can imagine a line as determined by two planes. We know that two planes actually intersect through a line. If two planes do not coincide and are not parallel, so if two planes actually intersect, then all the intersection points are on a straight line. So two different planes either have no points in common at all, or they have a line in common. I'm not talking about the situation when two lines are not different, when it's the same two planes.
Yes, but if the plane intersect a little, like not exactly on each other, like it's not right.
So if they actually, so there's no other
It's like
possibility. The
if
situation,
they
okay,
if they
at
intersect
an
like
angle,
that,
so one and
and they intersect, the next one intersect um like
okay, so that
like
it
that.
goes through it like this, you mean, like this. So the intersection is a straight line anyway, or they are parallel. They're either parallel. Imagine what happens. Take two sheets of paper. You can place them in a parallel way. You can place them so that you basically have a common line, one line, and that's it. Because if you want them to intersect somehow differently, then you have to bend the papers. So you cannot do anything else. You either have them parallel, no common points, or you can have a line in common, or they simply coincide, flat one on the other. That's the third possibility, but then you don't have really two planes. Then you have the same plane written with two equations. So with planes, well, perhaps paper is not a very good analogy. Imagine you take something hard, two pieces of cardboard, or two pieces of tin sheet, something that cannot be bent. Then you see that it's just this. You can have nothing else. Either nothing or one line, or they completely cover each other, and that would be coinciding. That's what saves us. Otherwise, the situation with planes would be rather difficult. And so when we have two planes that intersect through a line, this means that in principle, you could write down the equations of those two planes and say, okay, we have defined the line of intersection like this. One plane, A1x, B1y, C1z plus D1 equals 0. And the second plane, A2x plus B2y plus C2z plus D2 equals 0. So two planes, if they intersect, then the line of intersection is, of course, clearly defined. If the two planes are defined, all constants are known, then this line of intersection is also defined. The problem with this kind of writing down a line, the problem is that we don't see the direction, we don't see any point. We would have to somehow deduce something here. We would need to figure out something here. independently. The problem is that if you write the two planes, it's like a system that we have not solved, a system that we have not solved. And if we have not solved the system, we don't know those points. We cannot write the equation of this line separately. So you either use Gauss method to try to solve this system somehow solve the system using a parameter t, like we had the general equation in Gauss method, the general equation. The rank of this matrix is 2. The number of variables x, y, z, 3 unknowns, 2 equations, rank is 2, which means there are infinitely many solutions. That is, the system would have infinitely many solutions, and they are all, each solution is a point on this line, a point common to these planes. In principle, when we were solving those equations or these systems of 3 equations, whether we use Gauss method or Cramer's rule or anything else, if we have 3 equations of 3 variables x, y, z, in principle, what we were looking for the common point of 3 planes. When we solve a system of 3 equations and 3 variables, supposing we can use Cramer's rule and it has 1 solution. So what happens is actually we are perhaps finding the common point of the 3 planes. See, 1 plane, the other plane, the third plane. These three planes have 1 point in common. So when we solve a system of 3 equations, like we did in linear algebra in the first unit, what actually happened was it could be described as we had 3 planes and we find the common point for these 3 planes, like in the corner of a room, 2 walls and the floor, or 2 walls and the ceiling. What we did when we were solving 3 equations and 3 unknowns. But sometimes the system had no solution, which means there was no point common to all 3 planes. For example, it could have been that 2 planes are completely parallel, they have no points in common, and then we had a 3rd plane intersecting these 2. In this case, there's no single point that would be common to all 3 planes, and that gave us, for example, the situation no solutions, 0 determinant. Or there are other situations when this might happen, but there was also the situation where the 3 planes actually had infinitely many solutions. The system had infinitely many solutions. So you could imagine this as, for example, a nice little book. See, 3 planes. 3 planes, they have a single line, they have 1 line in common, so infinitely many solutions. Basically, when you wrote those general solutions, in fact, you were writing a description of the line of intersection of these planes. When you were writing, remember we said, okay, let z be equal to some parameter c, then y was equal to, for example, whatever, 3 minus 2c, and x was actually equal to, I don't know, 1 plus 4c over 7. We had things like this. What this means is this basically is a set of parametric equations for a line. If we split this part apart, 1/7 would be a coordinate of the point, and 4/7 would be the coordinate of the direction vector. So this is what we have been actually doing. We did not know this interpretation. We had not discussed what this actually means. Now that we are looking at planes and intersections of planes, we actually see that we have been doing this. So in principle, we might say that in this case, this is something very similar to the situation of 3 equations. When using Gauss method, we got the 3rd row of the matrix, all zeros. That meant infinitely many solutions, and then we used whatever is in the first two lines to write something like this. And that means this was that equation of a line. This was the equation of a line. So this means that in principle, we have already been finding intersection line of two planes. However, this is perhaps not the simplest and not the easiest way of doing this by solving a system of equations using Gauss method. However, it is possible. It is possible, but we will, not today, but next time, that is on Wednesday, we will see how else we can find the equations of a line of intersection for two planes. And now, all equations, a list of all equations that we have discussed today so far. So we had the vector equation, if the coordinates of a point and the direction vector are given, then we have this kind of equation. Second was parametric equations. C, using exactly the same points, exactly the same values, exactly the same numbers, still the same, x0, y0, z0, m and p. T is a parameter, meaning it's an independent variable, depending on which we can find a point on the line x, y, z. Then we had this canonical equations. The canonical equations again use the same points, the same values, the same numbers. So if you just remember which number goes where, which number means anything at all, then you would be able to write whichever of these three types of equations is necessary. So again, we use them depending on. In principle, the vector equation is probably the least useful. We developed this vector equation, the first one, because it is good for developing the parametric equations, and from there we obtained the canonical equations. That's the best merit of the vector equation. In practice, we don't really use it, because in practice, number 2, number 3, parametric or canonical equations are much better and more practical to use. And then we had an equation of a line passing through 2 points. Again, you can in fact do the subtraction separately to find the direction vector, and that would be easier. And finally, we had this 2 planes. This is bad in the sense that it does not tell us much about the line as it is. The numbers A, B, C, D in both cases, in both equations, do not tell us much about the line itself. We get much more information from the first kinds of equations. From number 5, evidently, we need to rework it, we need to manipulate it, we need to change it in order to get more information. Because as it is, okay, we have these 2 planes. So what? Now, how do I know where this line actually is? In which direction does it go? No idea at all. So we have to do a lot of work. If we have a situation where number 5 is given, then we have work to do. But that's next time. Now, what are these equations of lines used to? So first of all, we can use them to find the angle between 2 lines. So the angle between 2 lines is, of course, the angle between the direction vectors. If we have 2 lines in space, now this is interesting. In the plane, 2 lines were either parallel or intersecting. In 3 dimensions, 2 lines could also be neither parallel nor intersecting. That would mean, imagine we have a plane. We have one of the lines in this plane. One of the lines is in this plane, and this other line is not parallel and not intersecting. So actually this line, the other line, intersects the plane at some point outside the first line. This means that these two lines, yellow lines, these two, they are not parallel, because evidently if two lines are parallel, we could draw a plane through these two lines. These lines are evidently not intersecting, because we see that this second line actually passes through at some distance from the first line. So they don't intersect and they are not parallel. Such lines are called skew lines. Skew lines, not intersecting, not parallel. This is only possible in 3 dimensions, because in 2 dimensions we know two lines parallel, 2 lines intersecting. In each case, we can draw a plane through these 2 lines. But there are some lines or some pairs of lines through which you cannot actually draw a plane. They do not intersect and they are not parallel, skew lines. And so if we need to define the angle between skew lines, what's that? They don't intersect. How do we find that angle? If the lines intersect, yes, we can find the angle. If the lines do not intersect, then in principle, we think of the angle between these 2 lines as imagine that you could move one of these lines. Imagine you can move one of these lines so that it intersects the other line. So move it parallel to itself to the point where it intersects this other line. And then we can say, all right, that's the angle. That's where we see the angle between these 2 lines. If we can move these 2 lines parallel, keeping the same direction, up to some intersection point. So that would again be the angle between these skew lines, even when they do not intersect. And so we could say it's the angle between the direction vectors in some sense. However, we understand that the direction vectors could form an obtuse angle, and the angle between the 2 lines is actually always the smaller of the 2 angles, not the obtuse angle, but the acute angle, or at worst, the right angle, perpendicular lines. So that means we have to make sure the cosine is positive. So we take the direction vectors, we find the angle between these 2 lines, whether they intersect or not, is the smaller angle. So I'm writing theta there, the smaller angle between these 2 lines, as the angle between the 2 direction vectors. Again, the points do not matter. Exactly the same like we did in the plane, only in 3 dimensions, there's less opportunity to do that, less ways of finding the angle. Only the direction vector helps. So the angle between the direction vectors, the points don't matter, only the directions, So you see the expression here inside the modulus parentheses is the classical equation, the classical expression for cosine of the angle between 2 vectors. Only now, if it's negative, we put the absolute value on it, simply to make it positive, so that with positive cosine, we will always get the acute angle. If you leave the cosine, if you allow the cosine to be negative, then you will actually get the corresponding complementary angle. Or was it the supplementary angle? All right, next, 2 lines are parallel if and only if the direction vectors are collinear, exactly like it was with the lines in plane. But again, because in space, as you see, in space we do not have the slope. In the plane, we have the slope. We had lines kx plus b, y equals kx plus b, and we said, okay, k is that tangent between line and positive x direction. K is called the slope or the gradient of the line. In space, that does not happen. In space, we do not have a thing called slope. So we can only compare the direction vectors. And so if the direction vectors are collinear, that is, if the coordinates are proportional, then we have two parallel lines. No other way of checking. This is the only way of checking. And perpendicularity, of course, if the direction vectors are perpendicular. That is, the scalar product of the direction vectors is 0. So this much about angles between two lines. What else is there between two lines or lines? Distance from a point to line, which is again something that we will mostly discuss next time, because we will need to deal with lines and planes. So no formula, because we had the formula for distance from point to line in 2 dimensions in plane. We had a formula for the distance from a point to a plane in 3 dimensions, the D formula, but from point to line in 2 dimensions, there's no such formula. Unfortunately, there is no such formula for the distance from point to line. Doesn't exist. You have to do it step by step. And that would be, supposing we have this line given by the direction vector and a point, and I'm sorry, this is different, this is not the same. X0, oh, I'm sorry, I made a little bit of mess. Sorry, I have to change something. This will be X1, Y1, Z1. It's not the same point. I'm very sorry. It's not the same point, because X0, Y0, Z0 is some point on the line. So we have some line in the space given by this equation. So the point M is somewhere there, and we are not really interested. So this the point M with the coordinates X0, Y0, Z0 doesn't matter much from the line. We have some other point. This is not point M, we will call it P. From this other point, I'm sorry, I forgot, I did a copy paste and I forgot to change the names of the points. So from this other point, somewhere, not on the plane or not on the line, now we need to find the direction. So first of all, in the plane, that was easy to find the direction perpendicular to the line, because we had a formula for finding the direction perpendicular, the slope perpendicular, the slope of the line perpendicular to the given line, the direction vectors or normal vectors that we could use for the line. However, in space, first of all, we need to know, okay, perpendicular to this line, but we need to know in which direction to go. In the plane, as we see, in the plane, there's no doubt. But in the 3 dimensions, we could start from point M and go in many directions, and all these directions would be perpendicular to the line. We could go in this direction, in this direction, in this direction, in this direction. See, imagine many directions that are perpendicular to the line. And so first of all, we need to find the correct direction from M that would go exactly towards the line, because in 3 dimensions in space, imagine it's very easy to take, let's say, to go slightly at an angle and go past the line, not hitting the line. So that's the thing that we will do here. We will first of all find an equation for a plane passing through this point and perpendicular to the given line. That is the plane that here in my sketch looks a little bit like a cloud, and that's why I'm going to erase it and sketch it more like we are used to. So that plane, we are finding the equation of a plane that contains the point M and is in fact perpendicular to this line. in fact perpendicular to this line. How do we do this? Well, if we have the direction vector of the line, this was the vector S of the line, that is M and P, we understand that if this line has to be perpendicular to our plane, then we can use this vector as the normal vector for the plane. So this would mean as the normal vector of plane. Then we have the equation of a plane. Now we need to find the intersection point. We need to find this intersection point. Oh, that's now P. Okay, so I can mark this by whatever letter, it doesn't matter. We have to find this intersection point. That can be found by solving some system of equations, which is usually not very complicated, but best of all, it's done by expressing the line in the parametric form and then putting that parametric form xyz into the equation of the plane and finding the value of t. We will do that next time. So this is not something we will do today. Don't worry, I'm just giving you the plan today. And next time on Wednesday, we will actually do this in finer detail. And then, of course, we see the distance here. Here we have this distance finally. And if we find the distance, if we find the magnitude of the vector Pm here in this moment, then we have found the distance. So I have described this method now so that we don't have to spend too much time on descriptions next time, so that we can actually proceed directly to attempting to do this. And now we have a bit less than half an hour for exercises. So for practice, let's do some practice with lines. So first of all, the canonical equations for the line passing through a given point parallel to the z-axis. So I can even attempt to sketch it a little bit. Just a moment. Yes, now. So suppose we have, all right, this is the z-axis, this is the x-axis, this is the y-axis, the classical system of coordinates. We have point minus x minus y, that would be somewhere the negative, so it's somewhere there in the three-dimensional space, the point M. And we need to write the equations for the line parallel to the z-axis. That would be, the line would go like this, and it would intersect the z-axis somewhere and go on. Not the z-axis, but the plane, the xy plane. Somewhere, and then it would go on. Now, how to write the canonical equations? We have a point. What we need is, of course, the direction vector. The direction vector of this line, as you see, it's parallel to the z-axis. So we can say we could use the vector k, the unit vector on the z-axis. The unit vector k, 1 unit long, goes along the z-axis to be the direction vector. And the unit vector k has coordinates 0, 0, 1. So the canonical equations would be x minus negative 2 means x plus 2 over 0, yes, equals y minus negative 2, that is y plus 2 over 0, equals z minus 5 over 1. So in principle, what we see is that x, for all points on this line, x must be equal to minus 2, y must be equal to minus 1, and you can in fact imagine that, yes, that's where this line cuts the xy plane. And it's vertical, so any z value is possible, any z value, but for all points on this line, x will be minus 2, y will be minus 1, and z can be any number. All right, what happened? Oh, this happened. Okay. Next, very clear, passing through a given vector, canonical equations. Point is given, vector is actually given. The direction vector will be 3 minus 1, 6. So the canonical equations are easy to write. X minus 1, y minus negative 2, that's y plus 2, and z minus 4. And now the ratios, and now we have the coordinates 3 minus 1, 6 for the direction vector of this line. And that's it. So if you have a point and the coordinates of a direction vector, you simply write it down. So writing down the equations of the line is simple if you have the information you need. Next one, 2 points. So in principle, we can imagine the situation. We need the canonical equations. So point A, point B. So I would, in principle, I would prefer to do it this way. So I say, okay, the vector S, the direction vector will be the vector AB. That is 6 minus 3 is 3. Minus 1 minus 0 is minus 1, and 1 minus negative 2 is 3. So coordinates of point B minus coordinates of point A are the coordinates of the vector AB, and that will be the direction vector. And now I need to choose one of these 2 points, A or B, to be the given point on the line. Okay, let's take point A. And so we have canonical equations x minus 3, y minus 0, and z minus negative 2. And now in the denominators for the ratios, we write the coordinates of the direction vector 3, minus 1, 3. So what you can do alternatively is remember that these are, for example, x1, y1, z1, and this is x2, y2, z2, and use the fourth equation template. That was x minus x1 divided by x2 minus x1. Y minus y1 divided by y2 minus y1. Z minus z1 divided by z2 minus z1. And basically you get the same thing after simplifying. It's exactly the same. So you see, it's up to you which way you choose to do this. By the formula using x1, x2, x, and y and z and all those, or you just write down the direction vector from the 2 given points and write the canonical equations directly like this. So you can write it from this, or you can write the canonical equation from the classical form. That doesn't matter. The result will be the same. All right, next. This is a little bit difficult, but in principle, so the canonical equations for the line given by 2 intersecting planes. So what we can do with these 2 intersecting planes is think. First of all, we need to think about how exactly we can express an equation of a line using these planes. So one thing, remember, we need the direction vector of that, line. So suppose we have these intersections. Okay, I'm going to sketch something. One plane and the other plane, something like this. We have 2 planes, they intersect. We want to know the equation for the line of intersection of these planes. Now, to think in terms of vectors, I have the direction vector S of this line. But Now, what I do have really from these equations, what I do have are the two normal vectors. I have the normal vector of one plane and I have the normal vector of the other plane. So what is the relation between these three vectors? The normal vector of the first plane, the normal vector of the second plane, if this is plane 1 and this is plane 2. The two normal vectors they have. So what happens is, I hope you can imagine, you can see how the direction vector of the line is perpendicular to both normal vectors, because the line, the vector S actually lies in the first plane, therefore it must be perpendicular to the first normal vector. It lies in the second plane, and therefore it must be perpendicular to the second normal vector. And this is how we can actually use. So the direction vector of the plane, of the line, sorry, must be perpendicular to the first normal vector, and it must be perpendicular to the second normal vector. So what we can do is, we could remember, we know one vector at least, which is perpendicular to two given vectors. That is the vector product. If I take now the two normal vectors, normal vector n1 and normal vector n2, and find the vector product, not scalar, but the vector product, the cross product, then it will be perpendicular, it will be perpendicular to both normal vectors. That is, it will be collinear to the line. So it will actually give us one possible direction vector for this line. And then we can see whether we need to adjust it or not. So now let us multiply these two vectors. 2 minus 3, 5 times 4, 1 minus 2. So we would have, let's say, for the first coordinate, we use second and third. So 6 minus 5 is 1. The minor. Now for the second coordinate, remember we need to change the sign. And so 2 times minus 2, minus 4, minus 20 is minus 24. Change the sign, it becomes plus 24. And finally, for the third coordinate, we use first and second. 2 minus negative 12 is positive 14. Okay, nothing, it cannot be simplified because one of the coordinates is already 1. So we could say, so thus we have found the direction vector, 1, 24, 14. There are other methods of finding it. However, all other methods are much more complicated, including Gauss method, including solving by Gauss method. It will be more difficult to find the canonical equations of this line. This is the easiest thing. And I always try to give you the simplest, the easiest method there is for solving any kind of problems. So it's really annoying to have you complaining, oh, I didn't understand this, I had to look up some videos online, and then you pick the most unlikely, the most difficult method. That simply means that you are not listening in class. Now we have the direction vector. We need one point. So the direction vector is done. Now the next part, we need a point. We need the point A, x0, y0, z0. We have M and P, but we don't have a point. So we can, in fact, now choose any particular solution of that system. In other words, we can choose, for example, x value and find the corresponding y and z values. Or we can choose the z value and find the corresponding x and y values. So in principle, it's up to us what we choose, and what we find. So in general, you may choose whatever value for one of the variables, whatever you like. I would like to take z0 equal to 0. Why? Because z has the highest coefficient in the two equations. I simply think that perhaps this is, oh, sorry, I did it. I did the wrong thing. I have to erase these. That was not what I had to do. I will take the highlighter actually, and I will take the yellow highlighter. I would prefer to choose Z equal to 0. Why? Because Z has the greatest coefficient. See, 5. Z has 5 in the first equation, coefficient 5. So it would be nice to eliminate Z. Let's suppose Z0 is 0. We may choose whatever we like. We may choose whatever we like. And so we get an equation, a system rather, then that looks like 2x minus 3y equals minus 1. 4x plus y equals 5. Simplifying this system now, if z is equal to 0. And then we can say, all right, I could, for example, take subtract by elimination, multiply the first equation by minus 2, add to the second equation, or express y from the second equation, or use any matrix method, whatever you prefer to do to find the solution of this system. So in this case, I will simply multiply the first equation by minus 2, add to the second equation, x is excluded, so we get 7y equals 7, so y0 equals 1, and okay, x0, let's make it x, and x0 equals, looks like also 1, yes. So we have a point A, so we can use the point A with coordinates 1, 1, 0. For example, you may, as I said, you may choose any other variable, any value you like. Only if you choose some non-zero values, the equations become a little bit more complicated, a little bit more difficult to solve than this system that we had. But choosing x equal to 0, why not? If you choose x equal to 0, you would still be able to find some value for y and some value for z. Or if you choose y equal to 0, you would be able to choose some value for x and some value for z. They might not be integers. You might get fractions. You might get fractions, but that doesn't matter as long as you get coordinates, some coordinates for some point on the line, because this is something that we choose. We don't have choose by all means, it must be that point on the line, or it must be this point on the line. You choose, you find any one point on the line, any one point. And so the equation, the canonical equation, let's use the point A now, the third part of the task. So x, okay, x minus 1, y minus 1, z minus 0, so I'm writing nothing there. And the direction vector is 1, 24, 14. And this is the canonical equations for the line. So what might be different canonical equations? You could have different points. It would depend probably on the points you choose, on the values you get for the point, for some point on this line. The direction vector might have, let's say, greater numbers. You could have 2, 48, 28, for example. So generally, we tend to choose the smallest possible coordinates, and if they're positive, if possible. So in principle, the direction would be clearly visible that it is the same direction. A point, the coordinates that you find for a point might be somewhat different. They might be different. Now, how to prove that these lines the two lines are parallel? We would need to consider, and then we have perpendicular lines. Okay, so the problem with this is, but basically that is the main problem, finding the direction vector of this line. Again, Again, you see, this is the normal vector of the first line is 1, 1, minus 1, the first plane. The normal vector of the second plane, 1, minus 1, minus 5. So these are the two normal vectors of the first two planes. So from this, we can find the direction vector for the first line, that is as the vector product of these first two normal vectors of the planes. These two equations, in this case, remember, these are planes, so we must use the normal vectors and we must find the perpendicular vector. And that would be, so the first coordinate would be, eliminating the first two, we have minus 5, minus 1, that's minus 6. Second one, eliminating the second coordinates, minus 5 minus negative 1 is minus 4, change sign to positive, plus 4. And finally, minus 1 minus 1 is minus 2 as the third coordinate. So in fact, I would choose a better one, really. From there, I would prefer to choose a nicer, not some nicer numbers, but these are actually okay. You don't have to divide by 2 or minus 2 because we don't need the complete equation. What we need is only the direction vector. And the direction vector of the second line is, careful, you have to use the coordinates at t. The coordinates at t. So you see, these are the values of m and p. Not 1 minus 1, 2, but the parameters, the coefficients at t. So it will be 3 minus 2, 1. And now just compare 3 minus 2, 1, the coordinates of one of the direction vectors, and the second, minus 6, 2, minus 2. So the question is, if this is true, then the two lines are parallel. Because remember that two lines are parallel if and only if the direction vectors are parallel. But the direction vectors are parallel or collinear if and only if the coordinates are proportional. And here we see yes, the answer is yes, because the ratio is minus 1/2. So the answer is these two lines are indeed parallel because the coordinates of the direction vectors are proportional. Another one, proving that these lines are perpendicular would involve basically the same thing. Again, the two normal vectors for these two planes, just remember these are plane 1, plane 2, these are planes. These are not lines. So they have normal vectors, normal vector n1 for the first plane, 3, 1, minus 5, normal vector for the second plane, 2, 3, minus 8. Be very careful in the situations where one of these coefficients is missing. Sometimes you might get a 0, one coordinate in the normal vector, or both, or even or 2, not all 3. So the second direction vector for the second line, so this is line 2 and this is line 1, would be, again, the first coordinate from these four numbers, minus 8, minus negative 15 is plus 7. For the second, from these, from first and second, and let's remember that we will need to change the sign, minus 24, minus negative 10. Minus 24 minus negative 10 is minus 14, change sign, plus 14. And finally, the third coordinate, 9 minus 2, 9 minus 2 is 7. And now we have to demonstrate that the two lines are perpendicular. So the first direction vector is minus 1, 2, minus 3. And these two lines will be perpendicular if and only if their dot product equals 0. So you see, in one and the same exercise, in the same task, we needed to do, this was the vector product, the cross product of two vectors. We needed to use cross product to find one of the direction vectors, and then we need to use the dot product to establish perpendicularity. Remember, -1 times 7 plus 2 times 14 minus 3 times 7. So you see -7 plus 28 minus 21 is indeed 0. So from there, we can conclude that the two direction vectors, S1 and S2, are indeed perpendicular. So I want to stress one more time the difference between vector product and the scalar product or the dot product, because there are enough people confusing these and getting the wrong product sometimes. So a reminder for you so that you deal better with the examinations. Okay, we have 3 minutes. Let me just check what we have. Sorry, I just need to go one more time here. Coordinates of intersection point, distance from line to point, acute angle, parametric equations, intersection points, intersection, okay, this. All right, we will do now, I think, this one. Finding intersection points of the line given by this, again, two planes and the coordinate planes. And the thing is, we will not need to find the canonical equations for this. We do not need to find the canonical equations for this. So, all right, so these are equations. These are equations for a line. They are two planes, but basically any point on the line, any point on this line will satisfy, both those equations. And if it also intersects the coordinate planes, then basically we know that, well, we could imagine, again, we could imagine the system of coordinates, 3 coordinates, x, y, z. And we understand that this line intersects the 3 coordinate planes. For example, it intersects the xz plane somewhere there. Then it moves into the xy planes, this octant intersecting there, and then it goes down, 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 and finally intersects the yz plane and goes even further on. So there are intersections with all 3 coordinate planes, but let's remember, on the plane x, y, the z coordinate is 0. So we can put the z coordinate equal to 0 in that system and say 2x minus 3y equals 9, x minus 2y equals minus 3. Like this, and solve this mini system, this very small school system, and find the intersection point, with the xy plane. For example, times minus 2y would be, I think, y is 3 and x is if one, no, just a moment, times minus 2 for adding, yes, y is 3. And if y is 3, then x is it also 3? No, y is not 3 then. Okay, I wanted to be very quick with something, and then I just got slightly thinking about other things. Okay, so multiply the second equation by minus 2, we get minus 2x plus 4y equals minus 6. Add to the first equation, we get y equals 3, yes indeed, and then x minus 6 is minus 3, so x is also 3. 6 minus 9. Why did I get, no, it's not right. Where did I make a mistake? Somebody clever. Minus 2x plus 4y equals minus 6. I multiplied by minus 2, so this was plus 6, right? That's where I made a mistake. So we have 9 plus 6 is 15. That was the right thing to do. And if y is 15, then x is, looks like 27. Yes, now it's correct. I remember now the correct answer. So we have 27, 15, 0. That's the intersection point with the xy plane. With the, for example, xz plane, we would have to take y equals 0 and find the next intersection point. With for the intersection point with the yz plane, we take x is 0 and find the third point. So we did not really need to find the direction vector. We did not need to find the canonical equations for this line. So sometimes we don't need to go to the extremes and do that much. Parametric equation, parallel, this will be something very simple because we see that parallel to this line, it means we already have the direction vector. It must have, or it can have, the same direction vector. So the direction vector will be 2, minus 1, 3. And the point is 1, 3, minus 2. And so we have the parametric equations. X is, Y is, Z is. It's interesting to write everything at once. So the coordinates x1, x0, y0, and z0 are 1, 3, minus 2. I write them vertically. And then I add 2 times t times s. So it's 2 times t minus 1 times t plus 3 times t. And these are the parametric equations. These are the parametric equations of the line. So on Wednesday, we will have more dealings with both lines and planes, including how to find an intersection point between between line and the plane. Also, how to determine whether two lines actually intersect in space, because remember, they could be skew lines that do not intersect. They are not parallel, they do not intersect. So how to determine whether lines intersect at all? That's for the next time. No, not much theory next time, basically no theory, very little theory, but mostly practice, 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 exercises, exercises, exercises. So I will also upload the third home assignment either tomorrow or Wednesday morning so that you have your week to deal with that. So our unit test is taking place next Wednesday. Again, it seems that we will need to exchange elementary mathematics and regular mathematics, exchange the times so that we can get the unit test in all together. But I will actually be thinking about this. Perhaps I will just split you into two groups. We'll see. There are many people who are not attending lectures, so I'm not actually hoping for them to join for the test. And please remember, those who are taking elementary mathematics, this Wednesday, that is the day after tomorrow, we have the elementary mathematics second test. All right, that's it for today. I am going to upload the vector test results later today when I get home from work. Unfortunately, I probably won't have time before that, but when I get home in the late afternoon, I will upload my late afternoon. So for many of you, it will be late evening already. I will upload your marks.
Miss, when is the will there be a retest for vector test?
Retest for vector test. Yes, we can perhaps arrange, well, if you can be ready this Thursday, the 1st of April, then we can do it then.
Miss, I don't know, we don't have our marks yet, right? So I just want to.
Okay,
Well,
I will, well, you will know the marks tonight,
okay,
evidently. You will know the
Okay.
marks tonight, evidently, so we'll see. I
Okay.
can do the retake on Thursday, this Thursday evening, yes. We can
Okay.
do that. If not, then we can do it next week, next Thursday, perhaps after that. That's also.
Okay.
So probably next Thursday will be easier because then some people will want to do the unit test number 3 as well. Maybe. Who knows? All right. I'll see you on Wednesday then.
Okay, bye, Miss. Thank you.
My
Thank you, Professor.
Gmail. Homework number 2 to my Gmail. Why? Somebody sent homework number 2 to my Gmail. How nice. It was due a long time ago. Okay.